happening in front of you. If you don't even know, I'll show you, okay, the video which you can recommend to learn that. And but still, in the this is the only video which you would be needing to watch. Why I was like, cool. Cheapest flight with K stops. It says that there are n cities, and these cities are connected by number of flights. By so far itself, by seeing the picture itself, we would have recognized it's a problem of graph. Still, we will read the question. Now, you are given an array of flights where basically each flight says, okay, from to with this price. So this flight will go on from this 0 city to 1 city with the cost of this 100, okay, and basically it has from to with this specific cost, which is price. Now I'm also given 3 integers, source, destination and k, which means let's say this is my source, this is my final destination, and I can take at max k stops. Like in the actual while booking the flights in Google Flights or basically any other flights, you must have seen that they shows, okay, non-stop or 1 stop, 2 stop. So if you can afford to have at max, let's say 1 stop, so you can choose either 0 stops or 1 stop, let's say. So that is, it is saying, okay, if the person has a demand and he has a request that I want just at max k stops, that's it. So you have to tell him what is the cheapest price he has to pay, right? And again, he can accommodate k stops, at most k stops. He cannot go beyond k stops. Let's say if he asks, I can do 1 hop or 1 stop, so you can give him the flight with 0 stops or 1 stop. You cannot give him the flight with 2 stops because he cannot, he don't have that much time. So the first obvious thing is that, okay, cheapest price is the smallest cost. Smallest cost, I can represent the same thing as smallest distance, right? I'm just trying to relate it with what you know, right? So smallest distance from source to destination. So it is nothing but single source, shortest path problem. Now, as soon as you saw this word, you can apply simple Dijkstras. That is, you had been learning so far, right? And if you don't know Dijkstras, you can watch this simple video in which we will discuss about Dijkstras in short version, but entirely in very deep Dijkstras I have explained here itself. But let's say if you don't even know Dijkstras, still in this video you will learn about Dijkstras also. Now, what will happen that if you want to apply simple Dijkstras, what do? You just take smallest distance node or basically smallest cost node, right? So in the very beginning, I will push in my Dijkstras the distance of 0 and the node of 0, right? And then, okay, I will encounter, there's only one edge, so I'll encounter this and I'll put that in my the data structure used in Dijkstras, or basically the data structure used in designing a Dijkstras algorithm is priority queue or min heap, because we want to get the minimum distance out. This is distance, this is node. So we want to get the minimum distance out because we want smallest or shortest distance. Again, I have replaced my distance with price with distance. Anyway, both are same. So I will insert that in my min heap and say, okay, 100 is the cost to go to what? One node. Again, 100 is from the node 0. And from the node 0, existing distance was 0. So now he will say, okay, bro, I have taken 1 stop and now I have reached 101, which means 100 is the cost and node is 1. Now, again, I have another. Okay, Aryan, 1 stop is done. So shall I stop? Bro, stop meant, okay, 1 stop, final destination, which means, okay, my steps to reach will be 1 more than the stops. So this is actually the steps which you are counting. Okay, 1 step done and next step will be final destination. So stops, although you have completed your stops, your stop was 1, but still you have stop is something about stops is like something in between, steps is completing. So we can easily say that our steps will be stops plus 1. So I can do 1 more step, right? Because I have done 1 stop and lastly I can do 1 more step. So ultimately, if I want to do 1 more step, I know I have 2 options. Either I can go here or here. And as I know that, okay, I'll use simple, my priority queue, then I'll use 100, and this will actually become a 600 plus 100, it will become a 700, and I have reached the node 3, and this will become a 200 and a node 3. Now you have seen that, okay, you have reached in a shortest distance. Again, you are always keeping track of the shortest distance, and thus you can see that you have reached your final destination. So you might end up saying, okay, Aryan, I'll simply apply my Dijkstras, but that can be wrong. Although you can simply say, I will apply Dijkstras and thus I'll solve my answer. So by simply applying Dijkstras, you can simply say that my time complexity is O of E log E. Now, firstly, a disclaimer, people just read and just have an imagination that the complexity of Dijkstras is O of V plus E log V. That is what people think, right? Actually, if you have not derived this, you will end up seeing that, okay, maximum number of edges in a node in a graph can be V square. So the actual thing is, it comes out to be E log E. Then maximum E can be V square. So we replace by V square, and log of V square is nothing but 2 into E. Thus, it actually becomes E log V. So please understand how backward think work. And okay, you don't even need to do entire dry run stuff. Just that proof and stuff of your complexity, just entirely dry run on any complex structure. Which means, let's say if I ask you what you want to find the complexity, just dry run on this and see that how many edges you are traversing and how many nodes you are traversing, because you can see there are many edges rather than nodes are less. So with that, you can easily derive the complexity of Dijkstras. Now, coming on back, we know that, okay, we might end up taking, but it's a very simple example. Dijkstras worked here, but maybe not in future. So let's say I take a new example, that this is my graph. This is my source. This is my final destination. Now I ask you, I can take only 2 stops. Again, remember, when I say 2 stops, I can take actually 3 steps. When I say 2 stops, which means, okay, 1 step, 2 step, 3 step. This is valid. Again, I have taken 3 steps. Stops are 2, 1 and 2. Stops are 2. And other steps can be, okay, 1 step, 3 step, 1 step, 2 step, and 3 step. Again, these are possible. Again, there are many ways. You can also go from here, somewhere. But yeah, remember, steps are one more than stop. And you are taking steps and not stops. Now, if we apply a simple priority queue here again, then okay, I will have my source. I will initialize, okay, distance is 0, source is A. Simple. A distance, we keep track of distance and node. Then we will simply grab out the minimum element. So I'll grab out the minimum element. Now, if I grab out the minimum element, I will just simply say, bro, I grabbed out minimum, which was this itself. So for him, the distance is 0. And then I will just push on its neighbors. Neighbors are B and C. And if I say B is at 1 distance away from my D, and it is 5 distance away from my D, so I'll just push in a 1B and a 5C. Now in my priority queue, minimum element is 1, B. So I'll just grab this 1, B, and then I'll say, okay, distance of B is 1, and then again, I'm just going on again and again. Now I can simply say, bro, then I can just simply push back its neighbors. A is already visited, so I'll not push back it. Now B is not visited, sorry, C is not visited, so I'll just push back C with a distance of 2. Okay, distance of 2, I just push back my 2 and C. Again, as I grabbed out, so next element 2 will come in, right? If 2 will come in, so 2 distance of C will become a 2. And then because we are always keeping track of the minimum distance if we grab out the priority queue. Now again, remember, maqsad nahi bhulna hai. Our aim was that we have to take two steps. Now 2 stops, which means 3 steps. 1 step is done. Second step is done. Second step was done here itself when we take from here to here. Now in the 3rd step, this is the last step which I can take. Again, we will grab the minimum distance element, and thus I can see, okay, I can go here and here, so it will become a distance of 3 comma D, and this will become a distance of 12 comma E. So you might end up saying, bro, Aryan, I have reached my final element, which is E. So, and the minimum distance, and I have always been taking the minimum distance so far because I was using a priority queue. So my answer is 12 for E. Bro, sorry, it is wrong. Why it is wrong? Because if you see, okay, so far you know that by your answer of using a priority queue, by using existing priority queue, you are using a distance and element or node. This is what you are using. Now I'm saying it is wrong. And how I can prove it wrong? Simply by showing you any other path with 3 steps. Again, 2 stops, which means 3 steps, with 3 steps having a lesser distance or lesser cost. So I'll show you now. If I take a 5, 1 step plus 1 6 plus 1 7, with a cost of 7, I can reach here. So your 12 is a higher cost. So your answer is wrong. You are wrong now. Now Aryan, okay, which means I cannot use a priority queue. No, you can use simply, which means you can use your Dijkstras still. Make sure what was causing it to be wrong. If I ask you what was causing it to be wrong, what you chose? You chose minimum distance. Okay, minimum distance, and then minimum distance. This is what you chose. Right now, I'm saying choosing minimum distance is not a bad thing, because ultimately your maqsad, your aim is also choosing minimum distance. But one thing, why did not you try this path, this path, this path? Why did not you try this path? Because you are only grabbing the minimum distance. You never concerned about the steps. Okay, maybe I could have, because if I ask you to reach here, if you have to just reach here, then 1 1 and 1, it would have been much better. But this 5 1 and 1, this is much better. So you must also see that what is missing, in your aim, in your maqsad, what is missing. So now I realize that okay, this is wrong, it will not work. Minimum distance, I figured out it is 7 via this specific path. Now and firstly, like the exact same thing I showed you above, also the proof of the actual complexity of Dijkstra, please just know that part, because it will be used in further complexity analysis, that what you will derive. Again, you can easily say the complexity of Dijkstra's is E log E. It is not E log V. It is, or you can say it is 2 into E log V. It's again same as E log E also. Now, you know one thing, that you have to change something or add something or do something. What was missing in your above approach? Your above approach did not consider the steps. It considered only the distance. Aryan, how would I know that my approach did not consider steps? Because bro, at every point of time, you only focused on distance. You never focused on steps. Which means if you are focused, okay, in one step, how much is the minimum distance I can cover to my final destination point, considering him as the final destination. So kind of, I also parallelly have to keep track of steps, because I saw that okay, in 2 steps, I can say that at a point C, again, my answer is linked with the steps itself. For example, in your once, again, I'm not saying stops, I'm saying steps. Make sure that part. So I'm easily saying that okay, in two steps, my minimum distance to reach C was actually 2. 1, 2. But if I had to do only one step, then my minimum distance to reach my point C will be 5. So my minimum distance is dependent upon the steps itself. So rather than taking only distance and node, I will also take the steps itself. Now let's see how we'll apply the same Dijkstra again. So I take distance, node and steps with me. So in the very beginning, I am at A, node, sorry, distance is 0, node is A, steps is 0 itself, no steps taken. Now from A I can go on again. I will still use my priority queue, I will still use my mean heap, but now again my main aim of using a priority queue is to get the minimum distance out, but I'm also using steps now. So I will always grab the minimum distance, but I will operate on steps. I'll keep track of the steps. My main operation will be steps. So what I'll do, okay, and again this can be very confusing for those who have not learned Dijkstra's ever. So if you want the final solution, go and watch the last part, which is the BFS. But who are very curious to understand the basics of Dijkstra's, then watch this video. That will actually clarify all the doubts. Now we had our A very beginning, okay, we removed it and then we passed in and pushed in all its neighbors. Neighbors are 2, C and B. Again, B at a distance of 1. So B at a distance of 1, B node and steps are 1 now. C at a distance of 5 and steps are 1 now. Now again I will simply priority queue I'll still apply. What I'll do is I'll again grab the minimum distance element. I'll grab this at the next step, right? Same priority queue, but Aryan, where's the steps gone? Bro, that is the difference. I'll show you. In the existing standard Dijkstra's, what you were using earlier, so what you were doing, if you encountered a node having a lesser distance, then you skip it. What you were doing that time, right? If you encounter a node having a lesser distance and you are getting on that node again, you just simply skip that node. But in the modified Dijkstra's, when you also have to keep track of these steps or these stops, then I can simply say that, okay, if you encounter a node with a lesser distance and lesser steps, then only you skip that. If you encounter a node with a lesser distance but lesser steps, then you skip that. If you encounter a node with, let's say, more distance but lesser step, still you keep that. If you encounter a node with a lesser distance, more step, still you keep that. So that is okay. If you encounter a node with a lesser distance and a lesser step, only then you actually skip that node. We'll see with what we mean. So okay, in this we saw that okay, 1 comma b comma 1, which means one distance b node and one step will actually be taken out. So I can simply say, so far my steps for a was 0, and again at every point I was landing onto a node, I was checking, I land onto a node, okay, steps were taken as 0 for him. Then next again, and make sure landing onto a node was on the basis of distance, and you are keeping track of the steps. This is what you are doing. You are landing onto a node on the basis of distance because you are using a priority queue. So it will grab out the minimum distance, but you are keeping track of the steps. So both things you are handling at the same time. Now, okay, you grab the steps. Okay, B came in here. Now, next time what will happen? Again, he will go out. He will push back its neighbors. Neighbor is only C because A is already visited. So he will push back and say, okay, C distance of 2. C and steps are now 2. So now minimum distance in the entire priority queue, although you have C also waiting here, but he has distance more, so he will not get out of priority queue. Priority queue, it will give 2C2. So I will grab the and put the steps of C. As you can see, the steps of C are actually 2. Steps of C are 2, and that is a fact. I grabbed in the node C. Again, let's say if I would have asked you, bro, if the stops required would have 1, if I would have asked you, stops required would have 1, which means steps required would have been 2, which means as you can see 1, 2 steps. So as you have reached on the node C, and maybe the node C would have been the final destination node, so you know that you have reached the node C with the minimum distance, always keeping track of the minimum distance. So you always know that you have reached C with the minimum distance, and also you have also had the sufficient bandwidth of using these many number of steps. So you can simply return the answer from here itself, that for C the minimum distance or minimum price will be nothing but 2. But let's say you know your entire problem, basic problem, it was nothing but existing problem itself. You have 2 stops, which means you have 3 steps, and your final destination is nothing but this specific destination. Let's reach here itself. Now, as you saw that we had reached C. Again, we are keeping track of the steps of every node now, because distance is kept in the priority queue. Now, in the next step, I'll remove my C, and then I'll grab the next node. For C, neighbors are D and E, so I'll push back the neighbors of D and E. D will have a distance of 3. Node is D and steps are 3, for example, and the same for E. The distance will now become 12. It will be E and the steps are 3. Again, I'll grab the minimum element from the priority queue. Minimum element will be 3 comma D comma 3 because of the minimum distance. So I'll just simply say, okay, for D, steps of D are 3, and then simply go on. Then as I do this, I will again go and remove my D itself. Okay, I have gone, no worries. I'll again go and remove my D itself because it is a minimum distance element, and then I'll push back his neighbors. His neighbor will be a E itself. So I'll push back and say, now the distance will be 4, because you will see 3 plus this cost will be 4, and then a D will be the node, E will be the node, and then final steps, which means 3 steps plus 1 step, which will be 4 steps. So that will be your steps. But bro, it has exceeded the number of steps which I could have taken. Sorry bro, this cannot be taken. It has exceeded my steps. Again, stops allowed were 2, so steps required were 3. I cannot exceed 3 steps. So bro, this can never be an answer. Bro, simply continue. Get the next smallest element. Okay, this is done. Get the next smallest is 5. Oh bro, it is 5. Oh, so if it is 5, then I'll do one thing. Okay, simply remove 5. Oh bro, one thing. If it is 5, so I'll get and say, okay, for node C, for node C, the steps of C is 1. Steps have reduced. Although you can see distance is increased, but steps is reduced. So what you will do? You will overwrite the steps. You will say steps of C is now a 1. And because as I told you, you can overwrite, although distance has increased, but for sure it is obvious that you came on to node C, this step node C later on, because you saw that this came first because it has a lesser distance. But you can again come back to a node with a more distance but lesser steps. Again, if the steps would have been more, you would have ignored that, skipped that. but here the steps are less, so you have to take that into consideration. So I'll take that into consideration, and then I'll simply say, okay, the steps of C has now become 1. Now if I just push that, so again the neighbors are D and E, so again push back D and E with the new distance, and the steps have also changed, which means D, so steps were 1, so now steps are 2 and 2. Again, as you will land on to the new value, minimum value now is 6D2. So again, for steps of D, earlier it was 3, now it is 2. It can still be modified. So I'll say steps of D are actually 2. Now again, he's minimum, he'll go on to its neighbors, he'll be removed, and he will push back his neighbors. D will push back his neighbors. His neighbor is E with the steps of 3, 2 plus 1. And then new distance, which is 6 plus 1, 7. So now this will be 7E3. Now again, this steps is inbound. Now if I check on the minimum element, minimum distance, everything is going on 12, 15 and 7. Minimum is 7. So simply grab out this 7 for E, which is the final destination for you. This steps is inbound because you can choose 3 steps, which means 2 stops, 3 steps. You can choose this is good, which is E is the final destination for us, and 7 is the minimum distance which I could have grabbed, and thus my answer for this is nothing but a 7. And that's how you will just simply add your steps also in the picture, and that's how you will simply use your min, heap, or priority queue or Dijkstras algorithm. And that's how you can simply solve it with Dijkstras. People say it cannot be solved by Dijkstras, but they are just deceiving you in telling it is hard to understand how it will be solved. Again, with this understanding, you'll be very clear with how Dijkstras is actually working, or how it actually works, and how we can modify that to use in our requirement. But again, we will see the improvisation also, but yeah, that is how it works. Code is pretty simple. Firstly, we had the vector of flights, which means flight is from to a distance or to a price. So we convert that to a graph, simple graph, F to a T with the cost of D, simple adjacency list. Now if you don't know this part also, like basic part of how to convert that to a adjacency list and all that stuff, please go and watch BAP graph series by Aryan Mittal. Just write on YouTube BAP graph series by Aryan Mittal. You will get the playlist out, and that you can watch. Now we simply converted the array into our graph structure, adjacency list, and then we made the simple priority queue or of min heap. Now this priority queue is nothing but a vector. Vector will store distance, node, and steps. By default, in a simple Dijkstras, we only store distance and node, but now as a modification, we will store distance, node, and steps also. And also, as you saw, that I will keep track of these steps at every point. So now I'm keeping track of these steps, or you can say stops. I have put the stops, but you can say the steps. I'm also keeping the steps at every point of time. Now I'll do exact same stuff. While my priority queue is not empty, grab out the top, which means the minimum distance element from the priority queue. Get the distance of that element, get the node, get the steps, and then I will compare from the existing steps. If my steps are more, there's no point, because you saw that I will override when the steps are less. When the incoming step was 1 and the existing was a 2, then only I overrided it. But let's say if a step of 3 would have come in, I would have never overridden it, because if something is coming later on in future, which means that it is coming with a higher distance, because everything which comes in earlier will have a lesser distance, because it's a priority queue. So it is actually a basic understanding of a priority queue or a Dijkstras. Now, if something is coming in future with a more steps, please bro, simply ignore it. Or what if you have surpassed a number of steps? As I showed you, stops are k, so number of steps allowed are k plus 1. So if you have surpassed the k plus 1 steps, bro, please continue. You cannot, this is not a good thing. Continue, bro, continue. Now if not, then please override your number of steps. Okay, I overrided that. If you had reached your final destination, okay, if I have reached the final destination, simply return the minimum distance, because this is right now the minimum distance. Okay, simply return that. If not, then simply keep on pushing that in your priority queue. Simply go on to the neighbors and simply say, bro, distance plus price, add the distance plus price, and then simply neighbor and steps plus 1. Although you can also want to add a if condition, you can also add that if condition which you use in a standard Dijkstras. You can also add it here, but that will not have much effect. And that's how ultimately you will simply return your minimum distance. If you are able to encounter your destination. If not, then simply -1. And that's how in existing Dijkstras, it had a complexity of E log E. I proved you also, if you are in the habit of saying E log V, I also proved it is E log V also. I proved that also above. But now instead of E, we are actually going on to and trying for all the keys, because earlier your node was containing your distance and your node itself, and then you were saying, okay, you will go on to every edge and try for every edge. So you were saying it was E log E. Now we just added one more thing, which was steps. Now I am saying I had k steps, so now it will increase by k complexity, so it will be E into k log E into k. And again, we usually add a plus V also. If you had known that, we also write V plus E log V, like this. We also add a V. Why this V is added? Because if we say that the graph is disjoint, which means the graph is, let's say, have no edges at all, but nodes. So that's the reason we always add a V in the picture, right? And the same way space used, will be E into K plus V. V again for the same thing, that disjoint will be there. But the main thing is that earlier it was E log E, now it will be E into K log E into K. This will be the complexity of your Dijkstras. But again, Dijkstras can be implemented. But now, Aryan, can we improvise it? Or maybe, and if you are not much good with Dijkstras, you must have gone overwhelmed with how Dijkstras is working, how it is known, all this stuff. That can be very simplified if you understand that. Again, I taught you Dijkstras because the first intuition was single source shortest path. That is it. We always go by intuition, then we go by improvisation, right? So first intuition was Dijkstras itself. That's the reason I taught you Dijkstras. But it can be improvised by a very, very, very easy way, by simply using XYZ algorithm. How? Let's see. So if we look back and saw what happened ultimately while we were trying Dijkstras, remember, we had steps as 0 for A, steps for B as 1, then steps of C again came as 1. Then you saw it got overridden. Why? Because in future steps, okay, for a step 0, step 1 will be this, step 1 will be this, step 2 will be this, step 2 will be this, step 3 will be this, step 3 will be this. If you remember, this is what ultimately I was gonna try, right? The same way as we are moving level wise, okay, 1 step, 2 step, 3 step. Why can't this be done by simple BFS, which is breadth first search, level wise, right? So that's the reason I simply apply a simple BFS in this. And again, in simple BFS, you always go stepwise. Now, Aryan, if I apply simple BFS and as soon as I reach my final destination, shall I return the answer? No. Why? Because if you apply a simple BFS, okay, let's say I erase this. If you apply a simple BFS, and again, in a simple BFS, you will also have to keep track of the minimum distance. But let's say if you try out again, don't mix and match BFS and Dijkstras. They have a slight difference of how they work. I'll show both of them, but there's a slight difference. Your BFS always go level wise. It does not consider the distance. You have to manually put the distance as minimum. So you have to manually put an array or a vector saying distance, and that array you have to minimize. But in your Dijkstras, you by default always pick the minimum distance element. So here, if I go the minimum, so if I go in a BFS way, for him the minimum distance will be 5. For him will be 1. Then, if I am saying I'm allowed to do, let's say if I said, okay, my stops are not allowing me. This is the maximum number of steps which I could take. Okay, stop here. So for this answer is this. For this answer is this. But if I can do more steps, okay, do one more step, okay, this will actually be improvised. So it will become a 6, it will become a 2. So now if I say, okay, now the steps are stopped, okay, so for C answer is 2, for D answer is 6. You saw I minimized the distance here. Earlier I was minimizing the steps because I was using a priority queue. By default takes the minimum number of distance, by default it takes minimum distance. But now I am taking my BFS, it goes level wise. So level wise I am minimizing my distance. Okay, then at the third step I can say, okay, for this the distance is 3, for this the distance is 12, minimize the distance. For this the distance is my 7, for this the distance will be 12. So for sure 12 is large, so don't minimize it. So this will be the distance 7. So that's how ultimately you can say that you will get your minimum distance out. Cool. So just try on for this for all the key steps. It doesn't matter, let's say, as I showed you, it doesn't matter if you had reached your destination or not, which means if your destination would have been 5, but you are allowed to do two steps, which means one stop you are allowed to do. So if you had reached 5, let's say like this, in the very beginning your distance was 1 and 5. If you are still allowed, again the stops here I am saying are 1, which means stop R1, stop R1, so steps are 2 which you can take, steps are 2 which you can take. So you are still allowed to make one more step. So bro, please try it, don't regret in future. And let's say your destination is C, so please try it, which means as soon as you try it, the destination of C will actually become a 2, and thus you have minimized your distance. So I'll do the exact same stuff. Dry run, again dry run. For the first step, what will happen? From source you will get the minimum distance. For distance of C has become 5, your distance of B has become 1. Same way at step 2, your distance of D will become 6 from 5, and your distance of C will become 2 at step 2. Again remember, मकसद नहीं बोलना है our ultimate in the from the very beginning. The example which I took, the same example I am taking again and again for Dijkstras also and for priority queue also. So again it is 2 stops and the same graph, 2 stops in the same graph, right? Now coming on back, so at step 2 we had done. Now we'll just simply go back and say on step 3 I will say, okay, from here to here the distance will be a 3, from here to here the distance will be a 7, from here to here the distance will be a 12. Minimum is 7, so return me the minimum distance. And bro, ultimately you have done 3 steps, don't go more than this. Again you will try on and do for 3 steps only because your stops were 2, so try for 3 steps only and ultimately return the minimum distance. So the only change is that no matter what, you will do level wise traversal, but you will do that traversal until your all steps are exhausted, which means you will try for all these steps. So the graph remains exactly same. Now it's a simple BFS, but we are keeping track of node and the distance. So I'll keep track of the node and the distance, and the simple queue I take in for my priority queue. Now although in a standard BFS you only do while until your queue is empty, but I told you that you have to try in for all these steps and keep on minimizing until you can minimize it. So you will try in for all these steps. So while my stop is less than equal to K, remember you can actually have K plus 1 steps. So even if your step is K, still you can actually have one more step, so that you can have K plus 1 step. So it's the reason we have equal to here. Now as a simple BFS we grab the size because we want to have a level wise. Again there are many questions in which this thing is not required, but I highly say please follow a standard pattern for all the BFS approaches. Always go level wise. This indicates that I'm always going in level wise. I'll complete one level first and then only I'll go to my next level, which is the basis of your BFS. Now until your size is not empty, grab out the front element, remove that from the queue, and then simply go on to all of its neighbors. You have to minimize the distance. So check if the upcoming price plus distance, if it is more than the existing distance of the neighbor, continue bro, continue, because I have to minimize it, I don't have to increase it. So and if it is not continued, which means it is less, if it is less bro, simply update the distance of your neighbor by price plus distance and push that new distance in your queue itself, and thus you will just simply keep on pushing, but you will try for all these steps. And ultimately if your distance to that specific node which you wanted, final destination you wanted, if it is infinity, which was the by default value, then you will simply say -1, else you will simply say distance. Now complexity for this, earlier you know that your complexity for a simple BFS is you go on to all the edges, which means your simple BFS is O of B plus E, but now you know that you have to go and try for all these steps also. So even if your edge or your node is visited, still you will have to visit that edge again because of your steps, because you have to try for K steps, all, like no matter what you have to try for K steps again and again. So it will increase to E into K. And the same way, spaces will also increase to E into K. And that's how you can actually solve with your BFS. And the entire thing is, okay, you have to try for case steps for sure. Cool. By that, you have seen both BFS and Dijkstras approaches. It took a lot of time to make this entire stuff. So I'll highly like it if you can just like or smash the video. Cool. Thank you so much for watching. Bye bye. Goodbye. Take care. But make sure this video was for the ones who want to learn Dijkstras very carefully, because no one, I repeat, no one on YouTube has taught this portion. They have just made the video, but no one. Cool. Bye bye. Thank you. Goodbye.